So today is the last day of our unit about random walks on groups. And the goal of the day is to think about the Bourgain-Gamburd theorem about mixing on SL2FP. So we stated it at the end of last time. First, I'll remind everybody what it says. So it's about mixing on SL2FP. So it says if mu is a probability measure of SL2FP. Actually, maybe it doesn't matter that much, but maybe we said it in terms of subsets. OK. So the question is, when does the random walk coming from A mix? So then the conclusion will be the singular value of this walk is less than 1 minus c of epsilon, meaning that it does mix. OK. To see that this happens, we need to know that A doesn't lie in any subgroup. And so we have a hypothesis that's related to that. It says that for any Borel subgroup B, A intersect GB, so any G in our group. And this guy is bounded by K of epsilon P to the minus epsilon times A. So only a small fraction of A lies in any coset of a Borel group. OK. And we put in parentheses that A is symmetric. We don't really need it, but it also doesn't matter that much. And it will make things a little cleaner. Yeah?
The question about the difference between using A as a subset versus a measure. Is it possible to just kind of pass between the two cases by just weighting by different subgroup sets?
Yeah, that's right. So the question was, what's the difference between taking a subset or taking a measure? I think there's not that much difference. I think if you can use this as a black box and prove things about measures, I think we also could just use measures through the whole proof, and it would work fine. OK. So this proof breaks into the proof of this theorem breaks into two important pieces, which are both interesting and which are both connected in different ways to themes of our class. OK. So the first part says that if you just have pretty much any set and you do this random walk, the only way it can fail to mix is if it gets stuck in something which is sort of approximately a subgroup. So it can fail to mix if it's literally contained in a subgroup, and a little bit more generally, it can only fail to mix if there's a set which is a lot like a subgroup which contains a lot of the mass of the measure. OK, so let's try to write this down. So this is probably true for any group. I'm going to write it for SL2FP for now, and then as we talk about it more, let's keep our eyes open of what we actually used. Symmetric. And sigma 1 Ta is bigger than 1 minus. Here I'll put 1 minus epsilon. Then there exists some kind of approximate subgroup called H. Yeah, hold on. Let me adjust a little bit. Let me also say that A is pretty big. It is not too tiny. Then there exists some H so that mu tensored to some power of H is pretty big. And this H is sort of like a subgroup in the following sense. So H, if you multiply it by itself many times, for example 5, you could do more. This is less than p to the O of delta times H. And H also is not too big. OK, so if you had another group, you would have to adjust these things. But I think that's sort of minor. I think that's all you would have to change. OK. So if you have a set which is a decent-sized fraction of our group, and let's say it's symmetric, then either that random walks mixes, or there is some subset which is sort of like a group. And when you take k steps of your random walk, you have a high probability of being in this set. And this set is sort of like a group in this sense. And so there's delta and epsilon. Maybe at the beginning I should say this. And delta depends on epsilon when it's possible. All right. Any questions or comments about theorem 1? This theorem 1 is Bourgain-Gamburd, essentially. Cool. Yeah.
Where does the p to the 2.5 power come from?
Yeah. So what's significant here is just that this is significantly smaller than the whole group. And if we, yeah.
Does it mean kind of like a power of the size of group less than 1, or be like little o of the group? Would that be sufficient?
Right. Right. Yeah. So, OK. So this comes last time from this. So actually, it's also important that this is bigger than 2. So we had this important property of SL2FP that it's yeah. So this wouldn't work for any group. So we have this important property for SL2FP from last time that every non-trivial representation has a large dimension, and that had the property that if this thing had a small L2 norm, so it was like kind of decently well mixed, then we would get a spectral gap. And then if you kept going, it would become really, really well mixed. And that's crucially being used here. And so here you could put anything bigger than 2. And the point is that it can only go wrong by getting stuck in something of size really smaller than p squared. Because we know once it's spread over something of size bigger than p squared, then it's going to keep going and spread all the way. Yeah, thanks. Yeah. OK. Well, this theorem raises a question. Who are all the subsets H that are like this? This becomes a much nicer theorem when we can write them all down, and, or at least say something meaningful about them. OK, so theorem 2 says something about that. So this theorem is due to Helfgott, and it builds on Reshofsky. OK, so it says if H is a subset of SL2FP, and it has these two properties. So all of this stuff is smaller than p to the delta H. And H is at least p to the epsilon. You can kind of read that off from here. It's not going to get stuck in something smaller than A. And at most p to the 2.5. then the conclusion is that H is concentrated in a Borel subgroup or Borel coset. So then there exists a Borel subgroup B, an element G in our group, so that H intersect B is bigger than some small constant times H. So our proximate subgroups basically have to sit in a Borel subgroup. This isn't a complete classification because some of the subsets of B are approximate subgroups and many of them aren't, but it's a meaningful piece of information. OK, cool. So you put these two theorems together, you can prove that theorem pretty quickly. Yeah?
If this C, does it depend on anything, or is it universe?
Does it depend on anything? Let's put this here. Let's see, I have all these epsilons and deltas. Don't think it depends on anything. So I guess here there should be this, so that we can do this. So this is getting stronger as epsilon's getting smaller. Epsilon's telling us that our thing is not too small. And then I think that this is just a constant. I guess that does suggest that we could have said something stronger up there. Yeah. Oh, this is definitely H, not B. I think it's right. Yeah.
This is a question about kind of the choice of G. If when H is a symmetric subset, would that kind of imply that the sort of optimal G is always going to just be the identity? Because you think of H as kind of being centered in some way around the identity, so shifting a subgroup by kind of a non-identity element wouldn't change the intersection?
Yeah, so the question is, if H were itself symmetric, which in fact I think will happen in this setup, then maybe you don't need this G, and maybe it's actually only actual subgroups. I think that may be. So let me just describe that I'm not sure we need G. Right. Yeah, so a good example to think about is if you just take a coset of a Borel subgroup. And in the abelian world, a coset of a subgroup will be very small when you add it to itself. But in the non-abelian world, it's not so clear. So I'll make a remark. If H is a coset of a Borel group, then how big is just H times H? Well, it's G times B times G times B. And because it's not commutative, I can't bring this across. So it's not obvious that this is small. So I think this is, in fact, large. So based on that, I think it's likely that we don't need this. But it makes the proof a little shorter. OK, cool. OK, so I have a couple of big picture comments about this. One comment is, let's compare to the perhaps simpler setting of an abelian group. So we maybe have the group of the integers, or the group of the integers modulo p. Suppose we had a subset in there that had this property and this property. So when you add it to itself, many times it expands, but only by a little bit, by a small power of the size of the set. Then what can we say about the structure of such things? That's a big open problem in additive combinatorics. That's the sort of Freeman-Rouget problem. If you have something even smaller here, like log p or so, then there would be a classification that would have to look like a generalized arithmetic progression. But in this range, there's not a whole lot. There's nothing like a structure theorem that currently exists in this range. So in a certain sense, this is stronger information in the non-commutative world than we have in the commutative world. Of course, you might point out that this is not a complete structure theorem either, but this is a really strong piece of information about our group, and I think in some ways it's stronger than anything than what we know in the commutative world. Yeah. Another comment. So I'm not sure. So Reshevsky and Helfgott both worked on this. Reshevsky came from logic, and I think that he was interested in the idea from the point of view of logic of like an approximate subgroup. You know, like a basic thing we have axioms for is that, you know, axioms for a group. And what happens if you relax those axioms a little bit? What can you say? So, interesting question from the point of view of logic. OK, cool. All right, so the goal for the class is to discuss each of these things in moderate depth, probably without giving complete proofs. And they have quite different ideas, but in both cases, the ideas are related to stuff in our class. OK, so first let's talk about theorem 1. So on theorem 1. OK, so we start with the measure mu, which is mu a. And we notice that mu L2 squared is 1 over the size of a. So that's like, is at most p to the minus epsilon, because it was built into our assumptions here that a is at least p to the epsilon. OK, now let's start convolving mu with itself. And we want to see if we convolve it with itself enough times is what will happen to the L2 norm. So let's say mu2. So let's call this mu1. Mu2 is mu1 convolved with mu1. And in general, mu k plus 1 is mu k convolved with mu k. So we're convolving with this thing with itself many times, and we're going to see what happens to the L2 norm. OK, so recall that if at some point mu k L2 squared were to be smaller than 1 over p to the 2.1, then we would get that sigma 1 of t mu k was bounded by this. OK, and then we would get that sigma 1 of t mu. So mu k is mu convolved with itself 2 to the k times. So that would be p to the minus 1 over 10 times 2 to the k. So if k is not too big, we would get a spectral vector. So that's our plan. OK, so we keep doing these convolutions, and we watch what happens to the L2 norm. And at every step, maybe the L2 norm goes down significantly. In that case, we're happy. Or maybe it doesn't go down. In that case, we're stuck. And the stuck situation, we'll try to analyze it carefully and see that the stuck situation only arises because of this structure, this setup. So let me write that out. So let's say G stands for our goal, which is that mu k L2 squared is less than 1 over p to the 2.1. If we get there, we're happy. P will stand for progress. We're not necessarily there, but mu k plus 1 L2 squared is bounded by p to the minus delta mu k L2 squared. Okay. And then S stands for stuck, which means we are not at our goal, and we are not making progress. Not goal and not progress. OK. Cool. OK, so as long as we don't get stuck, we will reach our goal in about 1 over delta steps. So if S never happens, we reach the goal in less than 1 over delta steps. And no matter what delta is just a large constant, and that is enough to give the conclusion. So then, if you do a little calculation using this, you'll get a spectrum. OK, So suppose we do get stuck. Let's think about what that means. OK. So there was a comment at the beginning of the class that perhaps there's not a big difference between a set and a measure. Because if you have a set, you can turn it into a measure. And if you have a measure, you can look at the points where the measure is pretty big, and you get a set. And that's actually what we're going to do. So let's say that A lambda of mu k is the set of group elements for our group SL2FP, where mu k of g is approximately lambda. OK, so we can decompose our group into pieces where mu k has various sizes. And one of these sizes must have a decent fraction of the measure. So we choose lambda so that mu k of A lambda is around 1. So we've cut our whole group into maybe logarithmically many pieces. Their total measure is 1, so one of them has to be pretty big. All right. And now let's say AK is defined to be this set. Right. So what we've learned is that mu k is roughly uniform on AK, and AK has a good fraction of the total measure of mu k. OK, great. OK. So more or less, you could imagine that mu k is just the uniform measure on AK. All right, so now what would we learn algebraically about AK from the fact that we are stuck? That actually has a nice interpretation in terms of a previous character in our course, which was the idea of energy. So let's recall what energy means and put it in a non-commutative context, and we'll see that it sort of exactly fits here. OK, so let's say, so if we have two subsets, A and B in our group, the energy of AB is the number of A1, A2, B1, B2. These guys are in A, and these guys are in B. So that A1 times B1 is the same as A2 times B2. Energy AB. Now, this is the same definition that we saw before in the context of a commutative group. Our group is now not commutative, which means that it matters what order I wrote those things in. And so it matters what order I wrote those things in. So EAB is not actually the same as EBA. OK, but otherwise, it's a very similar looking definition. OK, and we can relate this to this setup. We can notice that EAB is I take the characteristic function of A, and I convolve it with the characteristic function of B. When I do that, if I evaluate this at G, it will tell me how many ways are there to write G as little a times little b. Now I'm going to square it, because I want to have how many ways. I have that many choices for this and that many choices for that. And sum over b. So this is this. OK. So notice, I took something, I convolved it by something else, and I took its L2 norm. That's the character that's involved in being stuck. So something we can say. OK, actually, so before we do that, let me make a little normalization. So remark, EAA is in between a cubed and a squared. Right, so the a squared comes from, I could take these to be equal, and I could take those to be equal. And the a cubed upper bound comes from, once I've chosen these three, there's at most one choice for the last one. OK, so these ones have a lot of additive structure, and the typical example is an actual subgroup. And these have very little additive structure. OK. So now let's relate to being stuck. So if we are in the stuck case for AK, for mu k, then we could see, how do I want to write this? OK, so mu k is essentially 1 over ak, this characteristic function of ak. And if we want to be rigorous, I guess we could say something like this. And if we say mu k convolved with mu k is larger than p to the minus delta mu k, this is equivalent to saying that the energy ak with ak is smaller than some p to the delta times ak cubed. Claim if we unwind this, we'll get this. So if we unwind this, we'll see an energy, the energy of ak. And this, this is almost the minimum possible value of the L2 norm. And so it's almost the, it's almost the, this goes the other way. So let me say that again. So this is encoding this energy. It's a lower bound for it. And the lower bound is almost the biggest it could be. So this energy is almost the biggest it could be. Yes?
Would that be AK squared if it's the lower bound for energy?
Right. No, so no, it's AK cubed. And this is a minus sign, so this is possible. Yeah. OK, so this just got copied there. And all right. So if you look at this L2 norm, these are probability measures. So this L2 norm is at most that L2 norm. So when you look at this inequality, this L2 norm is really pinched. It's at least a small fraction. It's at least a large fraction of mu L2 squared, and it's at most mu L2 squared. So it's just about as big as it could be. So this energy is just about as big as it could be. OK, cool. All right, so if we get stuck, there must be a subset of very high energy. And that is a step towards being an approximate subgroup, but it's not as strong as the conclusion of theorem 1. OK, so at this point, the story connects to some characters that we talked about when we were doing projection theory over finite fields. It relates to the Balog-Summery-Gowers theorem and the Plunica-Ruza inequality. So first of all, let me just recall what they said in the commutative case. And then this is a non-commutative case, so then we'll have to talk about what's actually true in the non-commutative case. OK, so recall that if we have A contained in Z a commutative group, then we have two important theorems, Balog-Summery-Gowers. Balog-Summery-Gowers says that if A has a lot of energy, then it has a large subset and the large subset actually has a small sum set. So this set has additive structure in one sense, but it has a large subset which has additive structure in a stronger sense. And then, once we have this, there's another important theorem, the Plunica-Ruza theorem, that says if A prime plus A prime is smaller than L times A prime, so L will be this, then you can also look at the sum of 3 of them or 4 of them or whatever. So I'll just write this guy is bounded by L to the 5th. You could put other things, you get the idea. OK, so So this sequence of theorems is important because it gives a sort of amplification of structure. So this assumption is that A has some additive structure in some fairly weak sense. And that implies that a big subset has additive structure in a stronger sense. And then, therefore, it has additive structure in an even stronger sense. OK. So if we were allowed to just apply these two theorems, then from this moment, we would get the conclusion of theorem 1. The conclusion of theorem 1 would be that there's some set H, which could have been AK, which obeys this. OK. So we can't do that because this is for a commutative group, so we need to talk about what happens in a non-commutative group. But I thought it was, we'll talk about that, but I also thought it was a nice moment to recall these theorems and reappreciate that they're important and useful and do something kind of neat. In our halfway through the course check-in email, when I asked people, what things that we did do you feel like they really sunk in and you understood them, and what things you feel like it was sort of maybe hard to remember what actually was happening. This theorem in particular was cited as something where it was hard. People did not feel like they remembered very well what actually happened. So we get to talk about it again. Cool. Yeah. Oh, I guess another thing you might wonder is, OK, this is logically stronger than this, but does it really matter? Later, when we look at theorem 2, we'll have a good example. Theorem 2 really requires this as an input. So we'll see an interesting example of why you might want this. OK. So let's talk about the Balog-Samrady-Garish theorem. So I will tell you, I guess first I should tell you what is true in the non-commutative world, which really looks pretty similar to this. And then we'll actually remember the proof a little bit to see if we can get the proof to sink in a little bit deeper. OK. So I'm going to erase this. And what I want us to remember is just that to finish theorem 1, what we need is a good version of Balog-Samrady-Gowers and Plunica-Ruja in the non-commutative world. All right. So theorem non-commutative Balog-Samrady-Gowers. So it says if A is a subset of a group G, and the energy AA is at least K inverse A cubed, then there exists a subset A prime and A, so that it's pretty big. And there are a few different things we could write, but actually let me call this A tilde. A tilde times A tilde inverse is not too big. OK, so it looks very little different. But let's take this opportunity to remember how the proof worked and see if we can get it to sink in a little bit more deeply. All right, so proof sketch. All right. So remember that the energy AA is the sum over all of our group elements of RAA of G squared, where RAA of G is the number of pairs A1, A2 squared, so that A1, A2 is G. that's the energy. OK, so for the energy to be large, there must be a lot of group elements G where this is pretty large. We'll call those popular products. So P, the set of popular products, this is the set of G where RAA of G is greater than k to the minus something times the size of A. So the size of A is the biggest it could be, and so they're almost as big as it could be. So they're quite popular. OK. All right, so it's an exercise to see that if the energy is really big, most of the energy actually comes from popular products. So energy AA is pretty much is more than half comes from. So half of the energy of A is less than the sum over G in the popular products of RAA of G. OK. And so this is having popular products, that's almost equivalent to having a lot of energy. Those are basically the same thing. All right. So then we'll do a little thought experiment. Suppose that every product was popular. Every product in the product set of A had the same number of representations. Well, that number of representations would have to be pretty large because there's a lot of energy. And that would tell us that A times A was small. OK. So then we would be done, and A tilde could just be A. But that's not true, because it's not true that every element can be written as a product in the same number of ways. So what we want to do, we're hoping to find a subset A tilde so that all the products in A tilde times A tilde, they all can be written as a product in lots of ways, or something in that speed. OK, so now let's make the popular product graph. So the vertices are G cross G. Here's a copy of G. Here's a copy of G. And we put an edge from A to B. So edge from A to B if A times B is a popular product. OK. And right. Actually, this is not a G by G graph. This is an A by A graph, taking elements of our set and looking at their products. OK. So not every pair is a popular product. They might not all be popular. But there are, by hypothesis, because there's a lot of energy, there's a lot of popular products. So the number of edges is at least, there are lots of edges in this graph. OK. So A tilde is going to be some subset over here. And the good feature of A tilde is that for every A1 and A2, both in A tilde, there are many edges. There are many paths. So let me draw it. OK, so let's say this is A1 and this is A2. And then we're going to think of paths of length 4 that go from A1 to A2. So there are many, more than something, paths of length 4 that go from A1 to A2 in our graph. OK. And how many? Well, from a typical point, there are about maybe 1 over k times a edges out. And so we have A choices, A choices, A choices, and then we have to go to A2. OK. So there was a graph theory lemma that we can choose a substantial set A tilde here that has all of these edges. And that was the hardest part of the proof. But it's exactly the same as before. It had nothing to do with anything being commutative. So I just, that part I won't repeat. So there was a lemma that we can choose A tilde so that this is true. And A tilde is pretty big. OK. Cool. So let's name everybody in the middle here. Let me actually rename these. I'll call these A and A prime. And then we go over here to A1, to A2, to A3. So we know A1 is popular. We know A2 times A1 is popular. We know A2 times A3 is popular, and so on. OK. And what this allows us to do is to write A over A prime in many different ways. OK, so A over, OK, I have to be careful because I'm in a non-commutative group. I think I want to write A, here, let's call this A tilde. A times A tilde inverse. So that's A times A1. And now I'll put A2 times A1 inverse. And now I'll put A2 times A3. And then I'll put A tilde times A3 inverse. So if we do this out, so this guy here is A1 inverse, A2 inverse. You can see cancellation, cancellation. And this guy here is A3 inverse, A tilde inverse. Cancel that. So that's this equality, so not difficult. But we've written it in terms of 4 guys that are popular. So this A2 times A1 is not just A2 times A1. It's a popular product. It can be written in many different ways. So A tilde A times A tilde inverse can be written as Z1, Z2 inverse, or maybe P1, P2 inverse, P3, P4 inverse, where Pi are popular. And so right. OK, and this can be done in many different ways. And the number of choices for the Pi is at least A cubed. OK, so the conclusion is that the size of A tilde times A tilde inverse is bounded by, I'm going to choose 4 popular guys. So that's P to the 4th. And then I've overcounted, because each person has now been represented A cubed different ways, and ignoring some factors of K. And so that's A. OK. OK, so I remember the first time I taught it, I struggled a little bit with the intuition of this. The first thing you might hope to do is to choose A tilde so that every product in A tilde is popular. They all can be written in many ways, just as a product of 2 things in A. And then there are clearly not so many of those. But I think it's not possible to do that. It's not possible to choose A tilde where every one of these products is popular in that sense. But by being a little bit more flexible, we've chosen a tilde so that every quotient can be written in many ways, not just as a quotient of two things in A, but many ways in this slightly more flexible framework. OK, any questions or comments? Yeah.
So why can't you get the same result for A times A if you just choose paths of length 3?
Yeah, I think you could get the same result for A times A if you choose paths of length 3, or A times B. Yeah, so OK. Yeah. Sorry, I maybe was not transparent about. So the thing with paths of length 3 still works. I think that might produce two different subsets. Actually, maybe in the commutative case, I actually should have had two different subsets, at least initially. It works fine. And the reason that I have A tilde times A tilde inverse, the motivation for that is going to come in a moment. And actually, I'm going to try to argue that this is better than A times A.
And just to clarify anything, the way you stated it before, the popular products here is the subset of A times A with the small projection. It was stated in terms of a subset having a large projection, then that leads to you can choose a subset of A such that the subset is small.
Yeah, that's right. That's right. So in the projection theory version, this would be the small projection, and there'd be some big piece of A cross A that projects here. Yeah. Thanks. Yeah. OK. Cool. So this is the non-commutative analog of Bialek-Samoredy-Gowers. It really looks a lot like Bialek-Samoredy-Gowers. And this inverse is because we want it. We probably could. We could also have had A tilde times B tilde if we wanted. OK. The situation with Pluna-Carusa is actually a little bit more complicated. So non-commutative Pluna-Carusa. All right. So let's ask a question. Suppose we have A as a subset of a group, and A times A is small. Does it imply that A times A times A is small? So this would be the natural analog of Plunika's inequality. And the answer to this is no. OK, here's the example. So let's say H contained in G is a subgroup. And A is H union one other element, which is not in the subgroup. Now, what happens when I take A times A? A times A is H times H. That's good. Plus, or union, H times G union G times H union G times G. OK, there's nothing special about these, but because G is only one element, all of this stuff is small. So we can see that A times A is smaller than 1, 2, 3, smaller than 4A, probably 3A. OK, but now, what happens when I take A times A times A? OK, now I have three factors. And so that concludes H times G times H. And in the non-commutative world, I cannot slide this over. And this is not so good. There's no reason for this to be small. And so the size of H times G times H could well be the size of H squared. OK, so that didn't work very well. What to do about it? There is a theorem that if A times A times A is small, then A times A times A times A is small. Yeah?
Does the counterexample that you showed kind of have an example in SL2 of P?
Yeah, it does. So H could be any subgroup, say a Borel subgroup, and G is not in there. And yeah, this will happen. So this could happen in SL2F. OK. So there's a theorem that if you assume that a product of 3 copies of A is small, then the product of 4 copies of A is also small. But that theorem is not immediately useful to us because we don't have any input that a product of 3 things is small. OK. There's another fix to this. Let's just think about this example and how we might fix it. So this example has a lot of algebraic structure. And this is the algebraically structured part. And this is garbage. And it would be helpful to separate A into the structured part and the garbage. So how might we do that? So let's look at. This is the continuing in the example. Let's look at A times A inverse. You could do A times. Anyway, this works a little bit better for A times A inverse. So what do we have? We have H times H. Actually, yeah. So we will eventually look at A times A inverse. But let's think about how we might separate this. So this set has different pieces. And we can, if we want to separate the algebraic part from the garbage, so we'd like to find this part and distinguish it from that part. How are they different from each other? Well, let's think about how many representations there are for each product in this product set. Any product in here has many, many representations. And the products here have only one representation. So this guy here is the set of popular products. And actually, once we identified it, the popular product set then is an actual subgroup and has a lot of algebraic structure. OK. So now let that motivate the following proposition, which is an analog of Finite. So it says if A times A inverse is less than or equal to Ka. So A inverse, that means take each element of A and take its inverse. And then if Q is the set of popular quotients, so it's the set of G, so that R A inverse of G is bigger than K to the something A. Then you can raise Q to any power you like. Q, let's say we do it L times. Okay. So Q has a lot of algebraic structure. And the proof has a similar idea of writing things in many different ways. OK, so proof. OK. Oh, actually, I think it's a little bit tricky. I think it should be that. OK, so the proof is, let's look at A times Q times Q is Q. Say, I'll illustrate the proof in L equals 4. Let's illustrate with L equals 3. That'll give you the idea. Times A inverse. So somebody in here can be written as little a. And now this is a popular quotient. So this is little a2 inverse little a3. And there are many choices. And then, actually, let's illustrate with L equals 2. And then we have, here we'll have little a4 inverse little a5. We have many choices. Here, how many choices we have? About a choices. Have about a choices. And then at the end, yeah, I'll do this. A6 inverse a7, about a choices, and then a8 inverse. All right. So to say better what I'm saying, suppose that I have an element of this set. Then I can write the element this way. And so I can say that x belongs to a inverse. So x can be written as, all right. OK, so x can be written in many different ways. And for each way of writing it, we'll notice that this guy lives in AA inverse, that guy lives in AA inverse, and so on. So it can be written in around a cubed ways as b1, b2, b3, b4, where the bi are in AA inverse. OK, so the size of this set, this is bounded by the size of AA inverse to the fourth. So I get to choose these b's. And now I've overcounted, because for each x, there are around a cubed different choices of how I could write it, divided by a cubed. And that is smaller than a. OK, there's one thing I hid at the beginning. Let me do it properly and then pause and see what people think. So we were given a times a inverse is small. And that implies that the energy of a inverse is large. This is stronger than this. And now I'd like to switch these. And this is actually the same as this. So even though I don't know a inverse times a is small, I do know that a inverse a has a lot of energy. And the reason I can switch them is if I have a1, a2 inverse equals a3, a4 inverse. That's a quadruple that's being counted in this energy. Let's just rearrange things a little bit. I divide by a3. a3 inverse, a1, a2 inverse equals a4 inverse. Then I will multiply on the right by a2. So that's a quadruple that's being counted here. Yeah?
Did you know that A inverse A has to be small because it's just the inverse of A element in A inverse, or A inverse?
Oh, yeah, maybe that's true. Yeah, maybe I made this too complicated. So these are equal, but you claim that actually A inverse times A is A times A inverse. So over here I have A1, A2 inverse. If I invert it, if I invert that, I get, what's the inverse of this? I should invert this one. I don't think this quite works. So I didn't manage to switch the order when I did that. But I can switch the order when I look at the quadruple. OK, good try. OK, so this is large. So therefore, there are lots of popular quotients. So Q is large. which is what we used here. OK, so both of these proofs have following high-level idea. There's a lot of energy around, so it frequently happens that you can write a product or a quotient in many different ways. And if you could arrange a set where every product could be written in many ways, then you could get a clean estimate for the size of the product set. And by playing around with the sort of products that you consider, and by some experience and craft and skill, we can get that to happen. OK, so this is the analog of Plünica's inequality. And the reason that it was sort of desirable to put A tilde inverse in Bourgain-Gamburd is that that thing is designed to fit into this thing. OK, so this Q is the approximate subgroup that we were looking for, which is the conclusion of theorem 1. OK, so this finishes the discussion of theorem 1. It was a pretty detailed proof sketch. And it is a somewhat different setup that shows the significance of the idea of like Bourgain-Gamburd and Plünica-Rusa and this combinatorial methods. OK, so now in the 15 minutes that's left, I'm going to try to say a little bit about the proof of theorem 2. And the proof of theorem 2, it also connects with themes of the class, and especially with how some estimates are different in the case of a prime field or the case of a non-prime field. OK, so let's do discussion of theorem 2. All right, I'd like to put us in the following framework. We're going to look at SL2 of K bar, where K bar is an algebraically closed field. You could imagine it's the algebraic closure of FP. All right, and we're going to look at subgroups of SL2 of K bar. OK, so let's remember some easy ones. We have a subgroup like this, where A and A inverse are in this field. We have the Borel subgroup. So that's A inverse T. And we have the unitary subgroup. So those are some subgroups. We can take conjugates of them. Actually, let me come back to that. OK, so yeah, so then we can do two general things. We can look at subfields. So I can take SL2K, where K contained in K bar is a subfield. Or you could take any of these with a subfield. Those are subgroups. And you could take conjugates. So conjugate any subgroup, you get another subgroup. OK, so that is a bunch of subgroups that we can identify without too much trouble that sit inside of SL2 of K bar. OK, and there is a theorem that says that this is not exactly, but reasonably close to the full list. OK, so Dixon in 1901 gave a full classification of these subgroups. And it's a little bit messy. It includes a variety of finite subgroups in certain cases and so on. And his theorem implies that if H is an actual subgroup, then either H is contained in a conjugate of SL2K, where K is a subfield, or most of H is contained in a conjugate of Borel. OK. And if we know from the beginning that we're talking about a subgroup of SL2 of Fp, a proper subgroup of SL2 Fp, it eliminates the first case, so we must be in the second case. All right. But Dixon's methods are, some of them at least, are not very robust if you replace the hypothesis of being an actual subgroup by something like H times H times H times H times H is pretty small. So here's a common example of a technique that we use to classify subgroups that does not do very well if we replace it by approximate subgroups. Example is there's the order of the subgroup divides the order of the group. That's really useful in 18701. You want to classify the subgroups of some group with 8 elements. But it is something like that is not going to survive an approximate subgroup in any useful way. OK. So the proof of theorem 2 is based on a rather different strategy for this classification that's due to Larson and Pink. OK. So let me say part A, which is the Larson and Pink strategy. All right. So we're going to think about how a subgroup intersects these subgroups. So if you take SL2K and you intersect it with one of these, it will either be empty, or it would just be identity or something like that, or it will be a subgroup that's like T0 of K. OK, so we're going to study H intersected with T of K bar, H intersected with B of K bar, H intersected with U of K bar. And we'll see the following behavior. The H intersected with T of K bar is roughly H to the 1/3, or big O of 1. So if I take SL2FP and I intersect it with this, I'll get T0 of Fp. There'll be about P of those, which is about the cube root of the size of SL2FP. If I take some crazy torus in the algebraic closure, that it may not intersect this except at the identity. So these are the two things that could happen. And then similarly with these. So they first proved that if you take an arbitrary group and you consider how it intersects these kind of fundamental algebraic subgroups, then it behaves a lot like it were SL2 of a subfield. And then building from this, they were able to see that actually it would have to be SL2 of a subfield. So that's their approach to the rough classification. Yeah. So this was a cool paper. In pure group, they weren't interested in approximate subgroups. They were interested in pure group theory problem classifying subgroups of SLD of K, or other like Lie groups over finite fields. And the complete classification is clearly hard because any finite group embeds in a permutation group, which embeds in an SLD of Fp. So all finite groups occur as subgroups of SLD of Fp for some d and some p. And so it's not really plausible to give a complete classification. Or anyway, it would be at least as hard as classifying finite groups to give a complete classification. But they were able to classify, I think it's like subgroups of SLD of FP, which have at least some size, like p to the epsilon or epsilon times d or something like this, the ones that are decently large. And that was in around 2000, so this really is a hard thing. OK, but it also turns out that their method interacts well with just assuming that h times h times h times h is small. So here, this whole argument works if we just assume that h times h times h times h times h. OK. I may or may not have like 2 minutes to try to describe what they do. Yeah, how this part A works.
Significance of the algebraic closure. Like, why, if we only care about subgroups of SL2 FP, what is the what information are you gaining from intersecting with?
Yeah. So the question is, why bring into play the algebraic closure?
Also, what is the algebraic closure of FP?
And what is the algebraic closure of FP? Yeah. I am. Right. OK. You do need this for the following reason that should be familiar to us, even as analysts. So suppose you have a matrix in SL2R, and you would like to diagonalize it. You'd like to look at its eigenvalues or whatever. Well, you can't necessarily do that in SL2R. Because the eigenvalues could be complex. So in order to diagonalize it, you might want to move to SL2C. And diagonalizing matrices is useful because you can classify matrices by their Jordan canonical form, and this is a convenient way to organize things. And that's the same thing that's going on here.
But like the intersections look the same though, right? Like the intersection of, if H is just a subgroup of SL2K, then the intersection with TK bar is the same as the intersection with TK.
Yeah, that's correct. That's correct. But OK, so the comment was that if OK, so what did this? So if H is in SL2K, then H intersected with T naught of K bar is the same thing as H intersected with T naught of K. Yeah, OK. I think the problem with it is that I forgot to say something about what's written on the board here. This T is not T naught. The conjugates are really important. So T of K bar is a conjugate of T naught of K bar. Yeah.
Might be elements that are being diagonalized, like just elements of SL2, or kind of bigger linear operators on SL2? I think if it's just SL2, you only need the degree 2 extension.
Yeah. So the comment is that if we just want to diagonalize matrices in SL2 FP, we probably only need a degree 2 extension of FP, which we might feel more comfortable with. I think that's probably right. I think we could probably work with the degree 2 extension. OK. All right. So the output of the Larson-Pink argument is after conjugating. OK, so yeah. So first of all, we can arrange that our H intersected with some unitary guy is pretty big. And after conjugating, we can arrange that this is U naught of K. So H contains some guys like this, where T is in some subset that I'll call E, and E is pretty big. OK. And moreover, this part is still should not expand too much when we take products. So here, let's call this thing sort of a unitary piece of H. UH times UH. Also, this isn't completely obvious, but it's not that difficult. It shouldn't be that much bigger than UH. And that tells us that E plus E shouldn't be that much bigger than E. OK. Also, we should have this U is in some B, and H intersect B of K bar. So we've already conjugated so that U is U naught. So this is going to be B naught. And this should be around H to the 2/3. OK. So and inside of there, we'll have a T. And H intersect that should be like H to the 1/3. So H intersect T naught K bar. That's going to be some guys that look like this. And these A's live in some set that I'll call F. OK. So then if you think about how these matrices act on these matrices, we should get, so T0, so let's call this guy T, the T part of H, and U, here. Well, OK. And this thing here is the B part of H. OK. So the B part of H times the B part of H should be not that much bigger than the B part of H. And if you unwind what that means, you multiply these, you'll have things like A inverse AT, where A is in F, T is in E. So the conclusion is that E times F is also not that much bigger than E or F. So in other words, once you have like a unipotent piece where you have these guys, then this multiplication operation just gives you addition of the numbers in here. So you have like a simpler thing. And then once you have a bunch of upper triangular guys, then this multiplication just gives you, this matrix multiplication induces this regular multiplication, and we have small products. OK. So this is consistent with the possibility that E and F could both be just some subfield K or some approximate subfield. But the sum product theorem says that FP has no approximate subfields. And so the subproduct theorem rules out the possibility that this could happen. So the conclusion is the sum product theorem implies that this can't happen. Yeah. Okay. Yeah. So what's on the board? I should add one thing. So we're going to assume that H is not contained in a Borel guy. Right. So this whole thing, that wouldn't be true for the Borel subgroup. It's only true once we assume that our subgroup is not contained in Borel. And then we get this. And that tells us that it has to look like the intersection sizes have to match SL2 of a subfield. And then if you look more carefully at what the matrices that appear in the intersections, you see that the entries there have to be kind of like a subfield. And then it becomes a question of whether there are approximate subfields. OK, let me say it one more time, and then we will break for the week. So the theorem says that if you have a subgroup which is not pretty much contained in a Borel subgroup, then it must be SL2 of a subfield. OK, so we would take, and it's going to be true for honest subgroups, but it's also true for approximate subgroups. So imagine we have an approximate subgroup. We're going to gradually prove that it has more and more properties of SL2 of a finite field. So the first property we will consider is how it intersects various algebraic subgroups of SL2 of k-bar. And the sizes of those intersections behave in a way that matches what you would expect from SL2 of a subfield. There's a substantial thing to say about this proof that we won't have time to do in this class. OK, but once you know that, these subgroups are useful because the matrices in here are simpler than general 2x2 matrices. So the unitary subgroup has matrices that look like this, and when you multiply them, you just add the upper right-hand corner. And so now, if you just look at these upper right-hand corners, you see that adding those numbers, it doesn't change very much. That's a property of a subfield. So it's behaving like a subfield. And the upper diagonal matrices, the multiplication rule is only a little bit more complicated. It's a pretty simple mix of multiplication and addition. So you could see that these diagonal entries, they should be almost closed under multiplication. And they interact with each other, and so you would get something like this. Anyway, all those things being consistent algebraically with being a subfield. OK, yeah?
We use 2.5.
Where did we use 2.5? Yeah, that's a good question. Actually, I don't see where we used that here. Yeah, we used that here. So at the end, we have to say E and F cannot be approximately a subfield. So, and that requires that they're significantly smaller than FP. So if you take FP and you remove like 2 or 3 elements, it is almost closed under addition and multiplication. So that would be, this could happen then if you were allowed to take a really large subset of FP and a really large subset of SL2 FP. OK, cool. I apologize for going over. Thanks for your patience. Have a good weekend. I will see you next week.